In this next problem, we are asked to consider two different designs. Now, one design puts all the circuitry into one design, one integrated circuit, one core, and that one has a area of 1 centimeter. So we have a big one, or we can break the design into two, and we can independently manufacture two dies. So the design consists of two dies. We're going to have to pay for both dies. So everything is the same. The wafers cost the same. The defects per area is the same. We're running this on the same assembly line. And so we're using the same wafers. They all have the same area. They all have the same costs, and they all have the same defects per area in the process. So really what we need to do is find out how much this one will cost at the end and how much this other one will cost at the end. And our ask is which design is better and by how much. All right, so you'd initially think, wait, this is much more complicated and there's more silicon area for design 2. You have to manufacture this, then you have to manufacture this, then you got to put them together on a chip. Well, together though, these are independent. So what we'll find is that the yields will be higher for these because the areas are smaller, plus we'll be able to fit more of them on a chip, or more dies on a wafer. So there'll be more of these dies on a given wafer, more of these dies on a given wafer as well. Initially, we might say that this is a much better way to do it because it has a smaller overall area, but we'll see how things shake up. So with this, we're really then needing to solve 3 different independent problems and then make a judgment call at the end. So we're going to consider design A, design 1, and design 2 is going to be broken into this, 2. So we'll call this the core. We'll call this the core 1. But then we're going to have core 2A and core 2B. And in order to get a working chip, then we're going to have both of those cores on there. All right, so now we just have independent calculations. What's the first thing that we want to do? We're going to say the number of dies per wafer. Number of dies per wafer. It's kind of nice. Everything's in centimeters squared here. Centimeters and centimeters squared. So what we'll do is number of dies per wafer. Well, that's just going to be the area of the wafer divided by the area of the die. And so for this one, the wafer is always 314 centimeters squared. We'll divide that. This is just 1 centimeter squared for the area. So this is going to be 314 dies per wafer. For core 2A, we've got 314, and we're going to divide it by 0.5, and that means we will get 628. That is 628 dies on a wafer. In core 2B, we're going to get 314, this is centimeters squared, divided by 0.6, and that's going to mean that we're going to be able to fit 523 of them. So fewer of the big dies fit on the wafer. So we get 314, 628, 523. That all makes sense. Next, we have to calculate the yield. Now the yield is going to be 1 over the 1 plus area of the die and the defects per area divided by 2 quantity squared. All right, so then this one, we're going to get 1 over 1 plus, this is going to be kind of hard to read, but the area of the die is 1 centimeter, the defects per area is 0.3, 1 centimeter squared, 0.3 per centimeter squared, divided by 2, quantity squared, and we get that the yield is 75.6% in this case. Next, here we do that same calculation. We're going to get 86.5%. I will let you verify that at home, and here we get 84.2%. So then 75, 86. Oh, now we're seeing one of the benefits of having smaller dies. We get more of them, but also our yield goes up. Now we find out the number of good dies. Number of good dies, that's going to be what we tried to make versus our yield. So this is going to be 314 times 0.756, and we get 237 here. We get 237. And here we're going to end up getting 543.4, and here we'll get 440.2. So remember, this is the number of good dies. We paid $100 for the wafer. We paid $100 for the wafer, and we got 237 good dies here, 543, 440. Now we ask ourselves, what is the cost per good die? The cost per good die in this case, well, here we get $100 is what we paid for, and we got 237 out, and so that's going to be equal 0.42. And then here again, $100 divided by 543, we get 0.184, and here we get 0.227. Okay, so for design one, all we need is this die. We're going to package it. It's going to cost us something to package the chip up and send it out. And we might get an attrition rate when we package because we might damage something. But we'll just consider the production cost of the dies. So this design is going to cost us 0.42 cents, or $0.42. That means 42 cents. However, to have a functioning, so for design two, in order to have a functioning chip, we're going to need both of these. So these will have to be added together because we're going to need one of each of them in order to get the actual functioning chip. So when we add those together, we get 0.411. And then we realize that, well, even though these had more of a area of silicon, because they were smaller, we got that boost from the yield, and we got that boost from more on a chip. So this is the cost for design 2, and this is the cost for design 1, and it turns out that design 2 is just a little bit better. So if we wanted to know by how much, we divide 0.42 by 0.411. Let's see if we can get that. We've got 0.42 and then 0.411. So this design costs this is 0.02 times design 1, design 2. So it's about, I always hate saying percent, but if you look at the ratio is 1.02. So if you want to say 2%, that's close enough to 1. And it turns out then that this is the better deal. All right, so then in your homework problem that you'll get, I won't give you how much the wafer costs, but really you're going to be doing the same analysis, and it doesn't matter how much the wafer costs. We can still get the percentage or the relative cost of the two, because in this case, the cost per good die was $100, $100, $100. If you want to just put in a dummy number, it'll end up coming out in the wash, or if you want to use a variable, it'll work as well.